So this started out with trying to add downlink values to the RAM archive, and we wanted to see what the granularity of the data was. So it took on a life of its own for me for the last couple of weeks. And one of the things we found was that the data is kind of maxes out at 10 Mbps. And that's what I wanted to talk about more. We'll also talk a little bit about effective connection type and the RTT. So very quickly, most people probably familiar with this. The browser support is mainly Chromium-based browsers. So Chrome, Edge, Opera, Chrome for Android, Samsung Internet. Those are the ones we see the most of in our data. And this is kind of what the API looks like when you call navigation.connection. You get downlink, which is in megabits per second with a granularity of 25 kilobits per second. Effective type, which can be 4G, 3G, 2G, or slow 2G. RTT, which can be anything from 50 milliseconds to 3,000 milliseconds. The cap on downlink and RTT are both to prevent fingerprinting. And save data was whether the never mind. I don't care about that. So I started looking at the downlink speed, which is here on the x-axis, versus the effective connection type, which is the color, red for 3G, blue for 2G, for 4G. And there's also some 2G and slow 2G in here, which you don't see because it's like one data point in this range. But essentially, what we found was the data is almost exclusively 4G, starting from about 1.55 megabits per second all the way up to the max, which is 10 megabits per second. It doesn't show. Yeah.
Can I interject one thing really quick? So the data that we're looking at here is across all of mPulse customers, I believe, or is it a subset of?
It is all mPulse customers. So 100% of mPulse traffic for a small period of time. So this is not a very large period of time, but I sampled it across multiple days to make sure it was consistent, and it is in fact consistent across the hour of the day, across day of the week, etc. So this is representative of the data we see across all customers. And the one thing that does stand out to me, apart from this sawtooth pattern, is the spike here at 10 megabits per second. And now this is a log chart. So what we have from here to here is about 150 times the population growth. So the effective connection type that we have is not really useful in segregating this data. They're kind of all competing for about 0.5% of the traffic at this level, and past that, it's not useful. If we did add another value for 5G, it would probably end up way out there. And the granularity of 25 kilobits per second, we really don't see that. We see a granularity of 50 kilobits per second. The only browser that does report this is a browser called Crosstalk that was, for some point of time, built by Intel, and I think it was end of life in, I don't know, 2013 or something, 2017. So we don't see that data anymore. So if when we move from this 9.95 to 10 megabits, we see 150 time increase in traffic. And that's where I wanted to concentrate a little more. So instead of looking at just the reported values, I looked at our own transfer size and download time data to calculate an estimated downlink speed. Now, the estimated downlink speed is supposed to be less than the advertised or the reported downlink speed, because there might be other hops in between that slow things down. But that's not exactly what we see. So in general, on the lower end of the spectrum, we tend to go with the 25th percentile. So that's this lower band here. It's the 25th. The darker band here is the 40th percentile, and the upper band here is the 50th percentile. So we're just looking at the lower 50% of data. And it tends to trend along with the 25th percentile until it gets to about this 6 megabits, and then it starts to trend with the 40 megabits per second all the way up to the max. And so I wanted to look at this a little more to see what the values should be for this 10 megabits per second range. And so I zoomed in a little more here, just going from the 9.8 to 10. And there are far more percentiles here, so 5th, 10th, 15th, 20th, 25th, 40th, and 50th. And we see that there's this jump up from here, right at the 9.95 to 10. Everything moves up, suggesting that the range of traffic is much more. The 40th percentile, which we were trending with up to this point, jumps up to 14 megabits per second, and the 50th goes to 20 megabits per second. So that's kind of where we're at this point. The recommendations that we have is first, we don't think that there's a risk of fingerprinting by increasing the cap. So moving from 10 megabits per second to 20 megabits a second, we'd still have enough data. Remember, this is 150x. In this case, I've shown the actual beacon count here. Right down here, it's up here, it's about 14 million beacons. Right down here, it's in the hundreds of thousands. So there's quite a huge range for us to reduce the likelihood of fingerprinting. Secondly, we do not need a granularity of 25 kilobits per second. I know it's in the spec. Nobody actually implements it at that level. We might, it might be useful to actually set the granularity much higher at 100 kilobits per second when we get to the higher ranges, because none of these 50 kilobit per second ranges actually make a difference. We see fairly similar beacon count across them. So that's what I have. Nick, you had something to add at this point.
Yeah. Along this, we're talking about the the network information API. The other attribute that we've been collecting in our bulk performance data is the effective type or effective connection type. Just for a refresher, this is just kind of an estimate that the browser gives. There's 4 total values: slow, 2G, 2G, 3G, and 4G, with the kind of ranges in RTT and downlink that are specified there. Philip obviously showed you some of this data, or how common some of these targeted ones are, with I think 4G accounting for the vast majority of all the data that we're seeing on the interwebs today, if that's right, Philip.
Yeah.
If you go to the next slide, if you don't mind, we've had some discussions around the effective type in the past, a couple years ago, and I believe some of the people on this call were part of those discussions, including Thomas Steiner, who was also doing a proposal for kind of updating it. So there's this open GitHub issue: should effective connection type be a fixed set of values? We circled around on it quite a bit. There's been some suggestions of like, could we add 5G, or change it to a fast, medium, slow buckets, or change buckets to be log-based, or stuff like that. With some decent ideas in there, I think. The conversation kind of died out in 2021. Thomas had a great kind of reboot proposal with some additional fields around being able to detect metered connections, which I think would be really great. Sustained speed over time. And just kind of as a reminder that there's a lot of different use cases for some of this data. People want to act on this data. There's like a Gmail use case where they could deliver light mode of Gmail or something similar, or not prefetch content, or yada yada yada. And there's also just an analytics case here, which is obviously important to Impulse from the bulk data. So I think, and bring this up just to say, I think it'd be interesting now that we're looking at some of this data, and we would like to surface some of it into the RUM archive public data set. What is the future of the some of these fields and classifications? The spec is just an incubation in WSCD, but it would be nice to kind of maybe modernize it a little bit. So wanted to get some feedback from this group, and just kind of feel like where everybody's at with their thoughts around it, both from the suggestions that Philip was having around the download link specifics, as well as the effective type, which I think a lot of our customers seem to be interested in using that data somehow to classify. So With that, I think that's all the presentation mode that we have, and it looks like we have a bunch of people that want to chat. So why don't we?
Awesome. Stopping the recording.